What's up, guys? It's Mr. Brengle, and today we're going to start talking about forces. And in order to do that, I want to start with the three laws of motion that Isaac Newton came up with. So jumping right into it here, Newton's first law of motion, sometimes more commonly known as the law of inertia, states that an object in motion remains in motion and an object at rest remains at rest unless acted on by some unbalanced force, which we will refer to a lot of times as a net force. First, understanding inertia. Inertia is not a force, it is a property of mass. It is directly proportional to an object's mass. So the more mass that an object has, the more inertia that it has. We'll watch a video about this that will hopefully help you guys understand that. But let's think about what would happen if we were to throw a baseball in outer space. Okay, and let's say that I'm in outer space and I throw this baseball at 5 meters per second. Okay, the reason I picked outer space is because there's no friction in outer space. The gravity's not acting on the ball, so in that environment, the ball would behave in the way that this first law of motion is talking about. This ball should travel on at a constant velocity of 5 meters per second until the end of time, or until it hits some other object. Remember, it says that it will continue to move in a straight line is really what that means. It will remain in motion in a straight line at a constant velocity until some unbalanced force acts on it. And so, that would be different from if I had a ball that was rolling on the ground. There's always friction that's acting on that ball. Well, that's a force, okay? So that is acting in the opposite direction, and it slows that ball down. And in outer space, you wouldn't have that. So conversely, if we had, say, a rock that was sitting on the ground, that rock is going to sit there and sit there and sit there, and it's never going to move until somebody comes up and decides to kick it with their clogs. These are clogs here. So somebody decides to kick the rock with their clogs, and then it goes off, right? But that object will stay at rest until it's acted on by some unbalanced force. Moving on to the second law of motion. The second law of motion states that the acceleration of an object is dependent upon the net force acting upon the object and the mass of that object. So I have these two equations up here for you, and it's really just the same equation. F equals ma is probably, if you've seen this equation before, you've probably seen it like this. It's a very famous physics equation. But if you rearrange it for the acceleration, it's force divided by mass. So you can see that the acceleration is directly proportional to the force. If you increase the force, it increases the acceleration. If you decrease the force, it decreases the acceleration. Also, and this should maybe make sense, if you were to increase the mass of an object, that would decrease its acceleration if the force stayed the same. And if you decrease the mass of an object and apply the same force, that object will accelerate more. So to kind of demonstrate that, think about if you were trying to push an empty box across the ground versus a box that was full of all sorts of stuff. It's really heavy. Got it from your attic. You try and push these two boxes across the floor. Well, certainly the empty box is going to be easier to accelerate, right? If we applied the same force over some period of time, we would just keep going faster and faster with that, and it would happen quickly. The heavy box, however, might take a little bit longer because it's got more mass, right? If we applied the same exact force, it's going to be harder to accelerate this object because it's got a whole bunch of stuff in it. Okay, so this equation is something you'll want to get comfortable with, and you'll want to understand those relationships that I was talking about. When we increase the force applied to an object, what happens? When we decrease the mass of the situation, what would happen if we apply the same force? That sort of thing. Okay, moving on to the third law of motion. The third law of motion is what a lot of people refer to as action and reaction forces. It states that for every action, there's an equal but opposite reaction. And those words action, I could also say this more like for every action force, there is an equal but opposite reaction force. So I've drawn for you here, this person is in a glass case of emotion, and this person is pushing on the wall here, this way, trying to get out of the glass case of emotion. Because that's a force that's being applied to the wall, technically, the wall also pushes back on the person, okay? Really the hands. I'm just trying to show the arrows away from each other. In fact, let me redraw that for you. It really should be like this, okay? So the wall pushes back on the person. It's no different than how, think about standing on the floor of our classroom, right? What would happen if there was nothing pushing back on your feet? You would fall through the floor, right? There would be nothing to hold you up. So you push down on the floor pushes back up on you. So to kind of show that here, this person is pushing down on the floor with their feet, and there is a force from the floor back up on the person, okay? I've also drawn for you here a person that's pulling a wagon, right? The person is pulling the wagon this direction. There's a force that's been applied. And then the wagon is also pulling back on the person, okay, with an equal but opposite force. Those arrows aren't necessarily the same length, but you guys understand what I'm getting at here. If that person pulls or pushes that wagon is going to pull or push in the opposite direction with an equal force, okay? Moving on here, just a couple things that you're probably going to want to take note of. The units for force are newtons, okay? It's just a capital N for Newton. And 1 Newton is equal to a kilogram times a meter over second squared. And, my hope is that that kind of makes sense, because remember that F, the force, is equal to the mass of an object times its acceleration. Well, if we were to do units here, a Newton is equal to a kilogram times meters per second squared. So that's all we've done here is instead of writing it as kilogram times meter over second squared, I just, you put the kilograms and meters in the numerator and second squared in the denominator. Okay, so I just want you to understand how those units break down. One big thing that we talk about in here is weight. Weight is a force. We designate it with capital F subscript G, and it's equal to the mass of an object times the acceleration due to gravity. Okay, and remember that G is always equal to 10 meters per second squared in this class. And it's an acceleration, so it matches up with this equation for force. A force is equal to mass times acceleration. Well, if you want to know your weight, you multiply your mass times the acceleration due to gravity. The fact that you're accelerating down at all times. Okay, a normal force. This is a contact force that acts perpendicular to the surface that an object is in contact with. So in our previous example, where the person was pushing on the wall that's pushing back on the person would be pushing perpendicular to the surface back out at the person. Similarly, if you're standing on the floor is pushing straight back up perpendicular to the surface of the floor back on you. We'll talk more about net force, but net force is talking about whether forces are balanced or not. So, like, for instance, if I had a box and I was pushing, let's say that I'm pushing to the right with 5 newtons, and then someone else is on the other side pushing back with 5 newtons, there would be zero force, net force there, right? Those subtract from one another. Those forces are going in opposite directions, so that box would not move. However, when net forces are not zero, meaning let's say that this time I'm still pushing 5 newtons, but the other person is pushing 10 newtons in the opposite direction, this object is going to start moving and accelerating to the left, because now there's a net force. F net is equal to 5 newtons left. Okay, so that will be important. We'll want to understand net force. So this is just a little bit of a crash course on Newton's 3 laws and a couple little extra things about force. We'll dive a little bit deeper into this in the classroom.